A syringe of white liquid empties into a vein in your arm. Someone asks you to count backward from 10. You say, 10. You say, 9. There is no 8. The next thing that exists is a different room, different light, different voices. 4 hours have gone, and you did not spend them. No waiting, no darkness, no long night to get through. 2 moments are pressed together with no seam. Here is what makes that gap difficult. Researchers have recorded directly from human cortex during that exact transition. The neurons did not stop firing. Activity continued. It simply stopped arriving together. And in an operating theater, under an anesthetic intended to remove awareness, patients have been asked a question with one hand deliberately protected from the paralyzing drug. Some of those hands answered. Afterwards, when questioned, those patients remembered nothing at all. So something disappeared. The question is what? Did consciousness end? Did it disconnect from the room? Or did it happen and leave no evidence that it ever did? Those are 3 different events. Medicine can produce all 3 on a schedule with a measured dose. It cannot yet tell them apart. Start with the assumption you have carried your whole life. You believe consciousness is one thing, a light that is on or off. You are here or you are not. An operating theater breaks that model within minutes. General anesthesia is not one state. It is a set of separate effects, produced deliberately, often by different drugs at once. Unresponsiveness. You stop reacting to your name, to a hand on your shoulder. Analgesia. The blocking of pain signals, usually a separate drug, most often an opioid. Amnesia. Not the absence of experience, but the failure to record it. Hold on to that difference. Everything later depends on it. Immobility. A neuromuscular blocking agent paralyzes skeletal muscle. It does nothing to awareness. It only stops movement. And autonomic stability. Keeping heart rate and blood pressure from spiking when the incision is made. An anesthetist assembles these. They can be dialed independently. A person can be immobile and aware. A person can be responsive and remember nothing afterwards. It is not a switch. It is a control panel. And this state is not sleep, though clinicians borrow the word because it is kind and roughly the right shape. Sleep often leaves fragments, a dream, grogginess, the sense of having woken from something. Proper general anesthesia can feel as though no subjective interval occurred at all. Sleep is generated by the brain itself, on its own schedule, in cycles with an architecture. General anesthesia is imposed from outside by a drug concentration, and it is not organized as a restorative biological cycle in the way natural sleep is. You can be woken from sleep. At an adequate surgical depth, ordinary external stimulation does not reliably restore purposeful responsiveness, even though early sensory processing may persist, which is the first hint that something more interesting is happening than a light going out. The drug in most of those syringes is Propofol. It is white because the active molecule does not dissolve in water, so it is delivered in a lipid emulsion. A standard induction dose reaches the brain in about 1 circulation time, roughly the time blood takes to travel from an arm vein to the head. Its principal action is understood. Propofol potentiates GABA, a mediated inhibition, across multiple receptor subtypes and brain networks. GABA is the brain's main inhibitory signal. Propofol makes that inhibition more effective. That is the molecular target, and it is not in dispute. It is also not the same thing as an explanation. A receptor account tells you why certain neurons become harder to fire. It does not tell you why a person's entire experienced world stops being available. Between those two statements, there is a large amount of missing narrative, and the intuition most people bring, that amplified inhibition produces a dimmer, a gradual fade to nothing, turns out to be wrong. In 2012, Laura Lewis and colleagues published a study in PNAS that watched the transition from inside the skull. The participants were neurosurgical patients who already had electrodes implanted for clinical reasons. That gave the researchers something almost never available: simultaneous recordings of individual neurons, local field potentials, and the cortical surface in a conscious human being at the moment consciousness became unavailable. Loss of responsiveness did not creep in. It arrived with the abrupt onset of a slow oscillation under 1 cycle per second, and the neurons kept firing. What changed was when. Spiking became compressed into narrow windows, locked to the trough of that slow wave. And different cortical regions had their troughs at different moments. Each region was still active. Each was active while its neighbors were not. The authors described this as a fragmentation of neuronal networks. So the light did not go out. Think about what that does to a signal trying to cross the brain. A message leaves one region and arrives at the next during its silent phase. Nothing is broken. Nothing is dead. The message simply arrives when nobody is listening. Do that everywhere at once, and you do not get a quiet brain. You get a brain full of activity that no longer arrives together. The timing of the electrical change and the timing of the behavioral change matched closely. Not minutes apart, effectively together. That is the kind of correspondence researchers look for, because coincidence is a poor explanation for it. It remains a correlate. A slow oscillation appearing at the same moment as unresponsiveness does not prove the oscillation removed experience. Both could follow from something upstream, but it replaces the question you started with. You began wanting to know what switches consciousness off. The recordings suggest nothing switches off, so the question becomes sharper and harder. What does a conscious brain do that an active brain does not? That question is not rhetorical. It has been the working problem of an entire research field for 2 decades, and it is unusually well posed, because you can specify what a wrong answer looks like. Any candidate has to be present in a waking brain, absent under an adequate surgical dose, and absent in the right way, matching the moment of transition rather than the drug concentration. Several candidates have failed that test already. Total electrical power fails. It does not drop in the right direction. Sheer amount of firing fails, as the intracranial recordings show. Activity in any single region fails, because no region has been found whose activity alone tracks the state. What survives so far is not a place and not an intensity. It is a relationship. Whether distributed activity can act as one thing, which is harder to measure than it sounds, and much harder to interpret. Before chasing that, notice a problem sitting underneath every study in this field. Each one needed a moment to label. This is where consciousness was lost. Everything before goes in one column, everything after in the other. How is that moment identified? By behavior. The patient stopped responding. A reflex disappeared. The syringe reached a certain volume. So the ground truth for research into consciousness is, in practice, a measurement of responsiveness. In an operating theater, that is entirely reasonable. It is the only practical signal available, and it works. For the question being asked here, it is a hole in the floor. Because think about what has to be intact for you to answer someone. You must receive the sound, process it as language, form an intention, move a muscle. And for anyone to know it happened, you must either be seen or remember it. Break any one of those links, and a conscious person becomes indistinguishable from the outside, from an unconscious one. Researchers separate the cases carefully. Connected consciousness means experience that includes the outside world. Disconnected consciousness means there is experience, but it is sealed off from the room. Reportability is a further step again. Experience never encoded into memory cannot be reported afterwards, however vivid it was at the time. You already know how strange that last one is because you do it most nights. Think about your last dream. Something happened. There was a place and events and some version of you inside them. None of it was your bedroom. The room existed. You were not connected to it. By any external measure, you were unconscious. There was still something it was like to be you. Now remove the memory, which is what happens to most dreams within minutes of waking. An experience occurred and left no trace. From the outside, and from your own later perspective, that is indistinguishable from nothing having happened at all. Anesthesia can produce each of these states, and it can produce them separately. A drug that suppresses memory formation without abolishing experience gives you an operation nobody remembers, and somebody had. A drug that removes movement without removing awareness gives you a person who cannot signal. Give both at once, and the patient falls silent in two directions. They cannot act. Afterwards, they cannot recall. Nothing about that combination is negligent. Both effects are given for sound clinical reasons, and the overwhelming majority of anesthetics do exactly what they are intended to do. But it means the outward evidence of consciousness can be removed while consciousness itself goes untested. And notice what that does to the phrase people reach for when they describe anesthesia. I was out. You did not observe yourself being out. Nobody has ever observed that in themselves or anyone else. What you observed was a discontinuity in your memory, reported afterwards by a brain that had resumed making memories. That is the only evidence any patient has ever had. The report is real. What it certifies is narrower than it feels. There is a way to test it, and it is almost crude. Before the paralyzing drug is given, a blood pressure cuff is inflated on one arm above arterial pressure. The drug never reaches that hand. Everything else is paralyzed. That one hand can still move. Then, during the operation, someone leans over and asks the patient to squeeze their fingers. The technique dates to the 1970s. It is called the isolated forearm technique, and it turns a paralyzed patient into someone who can answer. In 2017, Robert Sanders and colleagues published a prospective international multi-center study in anesthesiology. 260 patients were tested shortly after tracheal intubation. 12 responded to command, 4.6%. 5 of those 12, asked a second question, used the response to indicate pain. And of the 253 patients who could be questioned afterwards, none had explicit recall of anything. They responded. 5 signaled pain. Nobody remembered. Sit with the order of those 3 findings. Each is an observation. Together, they describe a state ordinary language has no word for. Now handle the numbers correctly, because they are routinely misused, including by people who are alarmed for understandable reasons. This measurement was taken at a specific moment, shortly after intubation, when stimulation is intense and drug concentrations at the brain are still moving. It is not a measurement of the whole operation. It does not mean that 4.6% of patients are consciously suffering throughout surgery. It means that at one probed moment, that proportion could respond to a command. A later international cohort of young adults, published in the British Journal of Anesthesia, found a higher rate, 37 of 338 participants, about 11%, with responses roughly twice as common in women as in men. Again, no participant remembered the commands afterwards. That 11% is also a time-specific response rate, not whole operation awareness. And responding to a command is not the same as the thing patients actually fear, which is remembering. That has been measured separately. In 2004, Peter Sebel and colleagues ran a prospective study across 7 American academic medical centers with structured post-operative interviews. Among 19,075 patients, 25 cases of awareness with recall were identified, about 0.13%. In the United Kingdom, the 5th National Audit Project took a different route, collecting reports of accidental awareness across the National Health Service. Based on patient reports, it estimated roughly 1 in 19,600 anesthetics. The two figures differ by more than an order of magnitude, and the difference is methodological. Interviewing every patient with a structured questionnaire finds more cases than waiting for patients to come forward. The audit also isolated the largest risk factor. With a neuromuscular blocking agent, the estimated incidence was about 1 in 8,200. Without one, about 1 in 136,000. That single comparison contains the whole argument. Paralysis does not cause awareness. It removes the signal by which awareness would have been noticed and corrected, which is why the monitoring question follows immediately. Processed EEG depth monitors exist. The bispectral index is the best known. They are clinically useful tools, and anesthetists use them. But major randomized trials did not show BIS guided protocols to be superior to carefully managed end-tidal anesthetic concentration protocols for preventing explicit recall in the studied high-risk populations. They are not direct consciousness detectors. They cannot be. A number derived from the electrical surface of the head is being asked to certify the absence of experience, something never directly measured in another person, in any setting, by any instrument. Every clinical judgment about awareness is an inference. A good one, made by trained people with a strong safety record. Still an inference. This is worth stating plainly, because the topic attracts fear that the evidence does not support. Awareness with recall is rare, it is taken seriously, and the risk factors are known and actively managed. The problem here is not that anesthesia is unsafe. The problem is that the thing being controlled has never been directly observed. So return to the question, now with the behavioral anchor removed. What does a conscious brain do that an active brain does not? The most consistent answer to emerge is about coordination rather than intensity. In 2010, Pierre Bouvereau and colleagues published functional MRI work in anesthesiology on Propofol-induced loss of consciousness. They reported a breakdown of connectivity both within resting state networks and between them, with thalamocortical connections particularly affected. Most sensory information reaching the cortex is routed through thalamic systems, while the thalamus also participates in recurrent coordination with cortex. The authors interpreted the pattern as a loss of long-range integration, not parts shutting down, but parts failing to act together. That distinction recurs almost everywhere afterwards. Local processing survives anesthesia surprisingly well. Play a sound to an anesthetized patient, and auditory cortex often responds. The ear works, the relay works, the first cortical stage works. What fails is what normally happens next: the spread outward, the reply from higher regions, the sustained exchange that in waking life turns a stimulus into a perception. The signal arrives and then goes nowhere. Several groups describe this as a breakdown of feedback. Information still travels forward from the senses, while return traffic from frontal and parietal regions weakens. That interpretation is not universally accepted, and measuring directed communication in the brain is genuinely difficult. But the broader pattern, inputs preserved, integration lost, has held across laboratories, methods, and species. More recent work has sharpened it. In 2023, a team publishing in PNAS showed that Propofol disrupts alpha rhythms in functionally distinct thalamocortical networks, rather than affecting the thalamus as a single undifferentiated block. Alpha does not vanish. It moves from the back of the head toward the front, coupled to the slow oscillation. And in February 2026, Yu-Chin Lee and colleagues published a connectomic analysis in Cell Reports Medicine using 128-channel EEG from 31 surgical patients with source localization. Propofol increased connectivity in the slow delta and theta bands and decreased it in alpha, beta, and gamma. When they modeled the transition, one measure tracked it most closely: alpha band connectivity between parietal, occipital, and subcortical regions. They propose it as a reliable neural correlate of propofol-induced unconsciousness. Note the word again: correlate. 31 patients is a real study and a small one, and a correlate is a signal that reliably accompanies a state, not a demonstration that the signal is what makes experience happen. No single rhythm has been shown to generate consciousness. What has been shown is that a specific pattern of long-range communication collapses at the moment a person stops being able to report a world, which is progress. It is not an answer. And then an experiment breaks the framework open by changing the drug. Propofol works by amplifying inhibition. Ketamine barely touches that system. It acts mainly by blocking NMDA receptors, and it produces an EEG pattern that looks nothing like Propofol's. Bursts of fast gamma activity, alternating with slow waves, described in detail by Oluwaseun-Akeju and colleagues in 2016. 2 drugs, 2 mechanisms, 2 electrical signatures. Both can leave a person who does not respond to anything. 3 outwardly identical silences. And if you knock on the cortex, 3 completely different echoes come back. That knocking is a real method. It comes from Adenauer Casali and colleagues, published in Science Translational Medicine in 2013. Rather than watching the brain passively, they perturbed it. A magnetic pulse through the skull, delivered by transcranial magnetic stimulation, and recorded the echo with EEG. The logic is physical. Strike the cortex and listen to the reply. A conscious brain produces a complex, widely distributed, evolving response. An unconscious brain produces a stereotyped one, a large local wave that dies out. They compressed that response mathematically into a single number, the perturbational complexity index. In 2015, Simone Sarasso and colleagues applied it to 3 anesthetics in current biology. Under Propofol, the pulse produced a low-amplitude slow wave. Local activation. Low complexity. Under xenon, a different agent entirely. A large, global stereotyped wave. Still low complexity. Under ketamine, the response looked like waking. Complex, spatially distributed, sustained. Then they asked the participants what had happened. After Propofol and after xenon, participants reported no conscious experience. After ketamine, they reported long, vivid dreams, with no relationship to the operating room around them. All three groups were behaviorally unresponsive. The measurement separated them anyway, and it separated them in the direction the reports pointed. Be precise about what that establishes. Complexity distinguished states associated with later reports of vivid, disconnected experience from states in which no experience was later reported. That is not the same as detecting the presence or absence of experience itself. Delayed report is not infallible access to everything that happened. Amnesia remains a live limitation, which is the entire lesson of the isolated hand. So the honest reading is that the perturbational complexity index is a promising state marker. It is not proof of subjective absence. Nothing here establishes that the Propofol and xenon participants definitively experienced nothing. What it does establish is heavier than it first appears. Behavioral silence is not one brain state. It is at least two, and they can be told apart by a measurement that ignores behavior entirely. Then there is the way back, which is usually described as induction played backwards. That description does not survive contact with the recordings. In a rodent study published in PNAS in 2014, Andrew Hudson and colleagues tracked cortical activity continuously through recovery. The brain did not retrace its path. It passed through a series of discrete, metastable activity states, each stable for minutes, with abrupt transitions between them, and some states acting as hubs connecting others. Recovery could not be predicted from drug concentration alone. To know whether the animal was anesthetized or awake, you also had to know the internal state of the brain. This was rodents, not humans, and it should not be read as an account of your own emergence. But it fits what recovery rooms look like. The intended endpoint of a planned general anesthetic is reversible emergence, achieved millions of times each year, and it does not arrive as one event. Orientation, memory, motor control, and the ability to hold a thought return at different times, sometimes in different orders. Anyone who has sat with someone waking has seen it. The eyes open before the person arrives. They answer a question and cannot answer it again 10 seconds later. They are told the same news 3 times. Whatever was lost was not one thing that can be handed back in one piece. It has to be reassembled, and reassembly follows a path that can be entered in more than one order. So separate what is established from what is not. Established, general anesthetics have well-characterized molecular targets. Propofol potentiates GABA, a mediated inhibition. Ketamine blocks NMDA receptors. These are not mysteries. Established, the transition to unresponsiveness comes with measurable, reproducible changes in large-scale dynamics, slow oscillations, fragmented firing windows, altered alpha rhythms, reduced long-range connectivity, reduced complexity of the cortical response to perturbation. Established, responsiveness, connected consciousness, memory formation, and later report can be separated by drugs, and routinely are. Not established. Which of those changes removes experience rather than reliably traveling alongside it? That is the open problem. Not that nobody knows how anesthetics work. A great deal is known. What remains unfinished is the bridge from a description of neurons and networks to an account of why one configuration produces an experienced world and another produces nothing anyone can report. That bridge is missing because nobody has yet worked out what would count as crossing it. Which brings back the syringe. Nothing in this story supports the idea that you went somewhere. No instrument has detected a departure. There is no place to look for, and no evidence of a passenger leaving a vehicle. What can be tracked is a reorganization, the capacity to receive the room, the capacity to bind what arrives into a single scene, the capacity to lay that scene down as memory, the capacity to report it. Those came apart under a measured dose, in a specific order. Then they were reassembled, in an order that is not simply the reverse. And here, the honest version becomes stranger than the dramatic one. If those capacities can be separated by a drug, they were always separate. The seamlessness you experience every waking second is not a fact about the world. It is a result being produced continuously by processes that can be taken apart one at a time. You have never had direct evidence that it holds together. You have only ever had the finished product. So what was the missing interval? It may truly have been empty, or it may have contained experience that never connected to the room, never became reportable, or never survived as memory. Anesthesia can erase the evidence either way. That is the part medicine cannot currently get behind, not because the science is careless, but because absence of response and absence of memory do not prove absence of experience. Count backward from 10. Say 10. Say 9. There is no 8 and no way from in here to find out whether that is because nothing happened or because whatever happened was never allowed to become something you could keep. Which of those is harder to accept is worth answering for yourself. Leave it in the comments.